Analyzing a main-to-main distribution system operating at 4160 volts reveals that paralleling two sources for brief maintenance periods doesn't drastically increase fault current beyond individual source contributions. This is because the distribution system's impedance and fault location limit the available fault current. It is recommended that upgrading all breakers, including feeders, to 350 MVA may not be essential. Consider these alternatives. Firstly, upgrade only the tie breaker to 350 MVA. This ensures protection during paralleling. Secondly, brace the buswork to withstand fault currents up to 350 MVA. Thirdly, maintain the existing main breakers at their current 250 MVA rating, because fault current through each main or busing is below the individual source contribution of 138 MVA, which means the existing breakers are adequate. This strategy balances safety and cost. By upgrading only the tie breaker and buswork, adequate protection is achieved without unnecessary expenditure. Further, ensure that the protection system trips main breakers before fault current hits 350 MVA at any fault location. Maintenance procedures should minimize paralleling duration. As system demand grows, contemplate upgrading main breakers to 350 MVA for added protection. In conclusion, upgrading solely the tie breaker and buswork to 350 MVA presents a logical, cost-effective solution for addressing safety when paralleling 4160 volt sources during maintenance. The existing breakers are likely sufficient, given the fault current limitations of the system. Ensure that the system is set to trip quickly under fault conditions and establish safe maintenance procedures. As the system evolves, reevaluate breaker ratings based on demand increases. This provides a balanced approach to safety and cost management. A detailed fault study is always recommended to ensure proper coordination and protection. Consider using protective relays that can detect and isolate faults quickly, thereby limiting the duration of high fault currents. Also, review the existing breaker maintenance records to assess their reliability and performance. Proper maintenance and testing can extend the life of existing breakers and ensure they operate correctly when needed. Evaluate the impact of any future system expansions or changes on the fault current levels. Any modifications to the system should be carefully analyzed to ensure that the protection scheme remains adequate. Consider using current limiting fuses in conjunction with the breakers to further reduce the fault current magnitude and duration. Current limiting fuses can provide an additional layer of protection and help to protect equipment from damage. Regularly inspect the buswork for any signs of deterioration or damage. Loose collections or corroded components can increase the impedance of the buswork and reduce its ability to withstand high fault currents. Train personnel on the proper procedures for paralleling sources during maintenance. Human error is a significant cause of electrical accidents, so it is important to ensure that personnel are properly trained and follow established procedures. Consider using a transfer scheme that automatically transfers the load from one source to another without paralleling the sources. This can eliminate the need to parallel sources during maintenance and reduce the risk of a fault. Evaluate the use of zone-selective interlocking to improve the coordination of the protection system. Zone-selective interlocking allows breakers to communicate with each other and trip selectively based on the location of the fault. This can improve the speed and selectivity of the protection system and reduce the impact of faults. Consider using arc flash protection to reduce the risk of arc flash injuries. Arc flash protection can include arc flash relays, current limiting devices, and remote racking systems. Regularly review and update the protection system settings to ensure that they are properly coordinated and provide adequate protection. Changes to the system or load can affect the fault current levels and require adjustments to the protection system settings. Consider using a power system modeling software to perform detailed fault studies and analyze the performance of the protection system. Power system modeling software can help to identify potential problems and optimize the protection system settings. Regularly test the protection system to ensure that it is operating correctly. Testing should include primary injection testing of the breakers and relays to verify their performance under fault conditions. Consider using a distributed generation system to provide backup power during maintenance. Distributed generation systems can provide a reliable source of power and reduce the need to parallel sources during maintenance. Evaluate the use of solid-state breakers to improve the speed and reliability of the protection system. Solid-state breakers can trip faster than traditional electromechanical breakers and provide better protection for equipment. Consider using a high-resistance grounding system to reduce the magnitude of ground faults. High-resistance grounding systems can limit the ground fault current to a low level, which can reduce the risk of damage to equipment and improve safety. Regularly inspect the grounding system to ensure that it is properly installed and maintained. A properly grounded system is essential for protecting equipment and personnel from electrical shock. Consider using a surge protection system to protect equipment from voltage surges. Voltage surges can damage equipment and cause it to fail. A surge protection system can help to protect equipment from these surges. Regularly inspect the surge protection system to ensure that it is operating correctly. Surge protection devices can degrade over time and need to be replaced periodically. Consider using a harmonic filter to reduce the level of harmonics in the system. Harmonics can cause equipment to overheat and fail. A harmonic filter can help to reduce the level of harmonics and improve the performance of the system. Regularly monitor the harmonic levels in the system to ensure that they are within acceptable limits. High harmonic levels can indicate a problem with the system. Consider using a power factor correction system to improve the power factor of the system. A low power factor can increase the current flowing through the system and cause equipment to overheat. A power factor correction system can help to improve the power factor and reduce the current. Regularly monitor the power factor of the system to ensure that it is within acceptable limits. A low power factor can indicate a problem with the system. Consider using a load shedding system to reduce the load on the system during emergencies. A load shedding system can automatically disconnect non-essential loads to prevent the system from overloading. Regularly test the load shedding system to ensure that it is operating correctly. A load shedding system should be tested periodically to verify that it will operate as intended. Consider using an uninterruptible power supply system to provide backup power to critical loads during power outages. An uninterruptible power supply system can provide a continuous source of power to critical loads such as computers and medical equipment. Regularly test the uninterruptible power supply system to ensure that it is operating correctly. An uninterruptible power supply system should be tested periodically to verify that it will operate as intended. Upgrading the tie breaker and buswork to 350 MVA provides enhanced protection during paralleling operations. Bracing the buswork ensures that it can withstand fault currents up to 350 MVA. Maintaining existing main breakers at 250 MVA is sufficient given the fault current limitation. The overall strategy balances safety and cost, achieving adequate protection without unnecessary expenses. The protection system must trip main breakers before fault current reaches 350 MVA. Minimize the duration of paralleling operations during maintenance. As system demand increases, consider upgrading main breakers to 350 MVA for added protection. Paralleling the two sources for a brief period during maintenance doesn't significantly increase the fault current beyond individual source contributions. This is because the available fault current is limited by the impedance of the distribution system and the fault location. This assessment is correct. The recommendation is to upgrade the tie breaker to 350 MVA and brace the buswork for 350 MVA while maintaining the existing main breakers at 250 MVA. This approach provides a balance between safety and cost effectiveness. By upgrading only the tie breaker and bracing the buswork, adequate protection is achieved without incurring unnecessary expenses.